Welcome. So we're going to be solving a couple more similarity problems in this podcast. A child 1.2 meters tall is standing 11 meters from a tall building. A spotlight on the ground is located 20 meters away from the building and shines on the wall. How tall is the child's shadow on the building to the nearest tenth? All right, so let's get a picture of this. All right, so there might not be a picture. All right, so you're going to read, if there's no picture, you have to draw it. All right, so now if you look at let's take a look at the diagram that we have here and kind of go through it so that if there is no picture, you could draw it. So a child 1.2 meters tall is standing 11 meters from a tall building. All right, so this, if I didn't have a picture here, I would draw. There we go, whoops. And my whole thing moved down. Let's just move that back up again there. All right, so I would draw a building. And so I don't necessarily draw a triangle at first. I just draw what's there. All right, so I have a building here. This is the building. And you should label your diagram the same way I'm labeling mine. Right? And a child is 11 meters away. Right? So this distance here is 11 meters. Here we have the child. Right? A spotlight on the ground is located 20 meters from the building. All right, so if we go from the building and go 20 meters out, we have a spotlight. Right? And so the spotlight is on the ground, right? And it's shining up. Right? And so it shines on the wall. Right? So when it shines, the light hits the child, and that creates a shadow on the building. Right? So over here would be the child's shadow. Right? And so the shadow is going to be taller than the building. Excuse me, not taller necessarily than the building, taller than the child, right? Because the shadow is further away from that light source, so it's getting larger. Right? So we want to find the height of the shadow, right? So what we're looking for is the height of the shadow. Make sure when you're solving this problem, you are comparing two similar triangles. Do not, and you don't have to color this part in, do not compare this triangle, right, to this trapezoid. Because I guarantee you, the trapezoid and the triangle are not similar. They're not even the same shape. They don't even have the same number of sides. How could they possibly be similar? All right? So make sure you know where you're trying. Draw them. And draw them separately. And actually, I'll draw them separately so that you can see them. Because every year, students do this. Somebody, not most people, not everybody, not most people, but somebody compares a triangle to a trapezoid. And you'll get an answer, but it's nonsense because the triangle and the trapezoid aren't similar. Right? So here's the one triangle. Right? There are two triangles formed by the spotlight and the child. The one formed from the spotlight to the child. Right? And then the other formed from the spotlight to the shadow. All right, these two triangles share a common angle at A. All right, so here, that angle A, these two triangles overlap. Right? So you have the smaller triangle that goes to the child and the larger triangle that goes to the shadow. They are overlapping. These two angles here are congruent to one another. Right? They're both formed where the shadow hits where the spotlight is. Right? And then the child and the building, which means therefore the shadow, are perpendicular to the ground. All right? So our triangles are similar using the angle-angle postulate. Right? Angle-angle similarity postulate. So we've got A congruent to A, and we've got B congruent to angle C there. Angle B congruent to angle C. And I'll even write that in. So we have angle A congruent to angle A. It's the same angle. And angle B congruent to angle C. And as a reminder why they're congruent, These are both right angles, and all right angles are congruent. And these would be congruent using the reflexive property. All right, so you can just write that in there. All right, so since you have two similar triangles, you can use a proportion to find the height of the child's shadow. All right, so let H be the shadow on the building, and then we draw a diagram as below. And then to help you, you can separate it out, right, and draw two triangles so that you can see all your measurements. All right, so, and I will tell you, 11 is not used in this problem. It's important, but it's not used in the problem. That would be the distance from like here to here, wherever the child is to the building. Not a side in a triangle. All right, so not being used. What we need is the height of the child and the shadow, and we need the distance of the child to the light and the shadow to the light. Right? So the distance from the child to the light is not given, but we can easily find it. Right? You subtract 20 minus 11, and the leftover is 9 meters. That's the measurement you need, the 9 meters. That's the distance from the light to the child. The distance from the light to the shadow is 20 meters. Then we need the height of the child and the height of the shadow. The height of the child is 1.2 meters. The height of the shadow is unknown. All right, and now we've set up our similar triangles. Make sure you're only using measurements in triangles, all right, not in trapezoids. 11's a measurement in a trapezoid. All right, so now let's solve. By the way, I could mix those up so long as I have a common thread. So long as height is compared to height, distance to distance, child to child, shadow to shadow. Let's just keep them like that because that one's perfectly good. All right. And I usually do child to child in one fraction, shadow to shadow in the other fraction, height to height in the numerator, distance to distance in the denominator. But if you want child to child in the first in the numerator, so long as you've then got height to height and distance to distance, it's fine. However, I'm keeping it just like this. All right, so child's height, 1.2. Child's distance is 9. One of the reasons I'm keeping it just like this is I usually like to have my unknown in the numerator. Not that it makes any difference at all. Shadow height is not known. And shadow distance is 20 meters. All right? So notice that I've got child compared to child. Then I've got height compared to height. And we've got a different color. Shadow compared to shadow. All right, just want to make sure that that was clear. Right? If you mix them up so you don't have a common thread, then your answer is also nonsense because you wouldn't have matched corresponding parts. I'm going to get rid of all these circles. Let's see if I can do it without erasing anything that's important. Yay, I did. All right, so there's nothing to reduce here. Let's just cross multiply. So we have 9x equals 20 times 1.2. We should get a calculator out. 9x equals, whoops. I said 1.2, but somehow I have 0.12. There we go. All right, so times 1.2 would be 12. All right, just move the decimal point over. So 20 times 1.2 should be 24. All right, and now we'll just divide by 9. All right, let's just reduce that. We can divide those both by 3. All right, that makes the dividing easier later on. We might put it in as a decimal if it's a terminating decimal. If it's not a terminating decimal, we can leave it as a fraction. Or in a real world problem, I am okay with the decimal, even if it doesn't terminate. All right, so if I divide both of those by 3, I have 8/3. So we can leave our answer as 8/3 meters. Or on a real world problem, if you want to put it to the nearest 10th, tenth, and I think maybe it says nearest tenth somewhere in here. I did not even hit that, so I don't even know how that comes up. All right, so we want to make it to the nearest tenth or nearest hundredth. 8 divided by 3. Right, well, 9 divided by 3 would be 3. This is going to be 2 2/3, or 2.67 meters. Right? So that's the height of the shadow. And that makes sense. It should be more than the child because the shadow is farther away. It is going to be taller, right? The light's going to keep on going. It's going to hit the child, and then the shadow is going to be it's going to just follow that same line, and it's going to be taller, right? Because the light is coming from below. It's going to make that shadow taller. And so our answer makes sense. All right, one done. Let's do one more in this podcast. Here we're using similar triangles to solve a problem. And this actually would work, by the way, what I'm reading here. To find the height of a dinosaur in a museum, Amy placed a mirror on the ground 40 feet from its base. Then she stepped back 4 feet so she could see the top of the dinosaur in the mirror. You can figure out height this way. Amy's eyes were approximately 5 feet 6 inches above the ground. What's the height of the dinosaur? Right? So long as you know how tall your eyes are from the ground, right, you can measure them, then you can find the height because the angle of your eyes looking into the mirror is going to be the same as the angle of the dinosaur in the mirror. Right? That is going to be a congruent angle there. All right? Not necessarily. Now, by the way, it's not drawn to scale here. Okay? Matter of fact, I plucked a photograph of a dinosaur here to make my triangle. So it's not necessarily drawn to scale. And these are, by the way, not vertical angles. Right? And then, of course, dinosaur and Amy are perpendicular with the ground. All right? So we're going to find the height of the dinosaur. Right? The mirror is 40 feet away. The dinosaur height is what we're looking for. I wonder if it will be easier to see if I write it in yellow or not. Depending on where I write it. I know, I have the lights on right now because it's dark. Yes, the red is just as good. All right, so we're looking for x. Remember, units must be in the same in the numerator and denominator. 5 feet 6 inches, that's not going to work for us. But it's not too hard to figure out because 6 inches is half a foot. So let's make that 5.5. Right, and then all is good. Now we just need to set up a proportion. All right, so now we have to compare like things. Distance with distance, height with height, Amy with Amy, dinosaur with dinosaur. All right, we're looking for the dinosaur height. So let's put dino height in the numerator. Let's put dino height right here. You can either compare dino height with dino distance, or you can compare dino height with Amy height. Whichever you prefer, it makes no difference. We'll put Amy height here. So it's height and height. That's what's in the first fraction. If I put dino height in the numerator, it means I'm going to have dinosaur all across the numerator, and I need dino distance. Dino distance. And of course, that means Amy distance is going to be in the denominator. So you see we have in one fraction we have height, the other fraction we have distance, numerator is dino, denominator is Amy. Let's replace the descriptions with numbers. The dino height is what we're looking for, that's an unknown. Amy height is known. She's 5.5 feet tall. Well, her eyes are anyway. She's pretty tall, actually, for a girl. Or who knows, maybe she's a woman. Maybe she's fully grown. And now dino distance is 40 feet. Amy distance is 4 feet. Well, while you don't have to reduce, it's not a requirement. You really should reduce the 40 and the 4, give you smaller numbers. You would get the same answer if you didn't, but I think I want to make that 1 in 10 because 4 divides evenly into 4 one time, and 4 divides evenly into 10 1 times. And that makes for a really easy problem to solve. 1 times x is x. 5.5 times 10 is equal to 55 feet. And I have no way, my picture here is Tyrannosaurus Rex. I honestly have no idea how tall Tyrannosaurus Rex is and don't really know if he'd be 55 feet tall. Maybe he's taller, maybe that's right. I really don't know. That seems reasonable to me. And that's the last one I'm going to solve in this particular podcast. By the way, if you ever want to check your answers, you can always plug it back in and see if you get a true answer, a true proportion. Of course, that will only tell you that you solve for your variable correctly. It's going to, whether or not your answer is correct is going to depend on whether you set up the problem right. So remember, match the, you have to have a common thread in the numerator, the denominator, and each fraction. So long as you do that, and you make sure that all your sides are from triangles, and you match up the corresponding ones, you'll have no trouble. All right, thanks for watching. Bye for now.